So in the previous section, we discovered that we could write a surface current density as the cross product of the magnetization with the unit normal vector to the surface, and a bound volume current density as the curl. And so these quantities are really, this is really analogous to our development of electrostatics. In electrostatics, we found that we had a bound volume charge, which was minus the divergence of the polarization, and a bound surface charge, which was the dot product of the polarization with the surface normal. Now, in electrostatics, we argued that these charge distributions were real. That is, that if we had a material with a polarization, that we would in fact have a bound volume charge, a real bound volume charge given by this quantity, and a real bound surface charge at all the surfaces. On all the surfaces, perhaps maybe a surface charge here, and we could have charges on the other surfaces as well, which was given by our equation on the previous page. And in an analogous way, if we have a magnetic material that has some magnetization, we do indeed have surface currents and volume currents. So we have a volume current density, JB, which really is this quantity, and surface current densities. So these are bound current densities, if you like, that are in the material, and surface current densities flowing on the surfaces, let's say, and these are given by our formula, which is the cross product of the magnetization with the surface normal. Okay, so let's study these in a simple geometry, in a simple context. Imagine we have a cylinder, a magnet. Let's make it a magnet, maybe a rare earth magnet, and it's cylindrical in geometry. And let's say it's got a magnetization M in this direction, and we'll make it constant. So constant magnetization, and we could ask what are the surface bound currents and the volume bound currents in the system. Well, if we look at the surface normals, the surface normal here on this surface is in the z hat direction, and the surface normal on this part of the cylinder, all around the cylinder, is in the rho hat direction. All right. So first of all, if we were to calculate the volume bound currents, JB, this is equal to the curl of M. Well, this is the curl of a constant vector field, so this is clearly going to be 0 in this particular case. For the surface bound currents, we would take the cross product of the magnetization with the surface normal. So if we were to take the cross product of the magnetization with this surface normal, we're clearly going to get 0. Z hat cross Z hat is 0, and there are no surface currents flowing on this surface. However, Z hat cross rho hat is not 0, so let's calculate that quantity. Right, well this, if we were to calculate that cross product using the right hand rule, we would get M phi hat. Okay, so in other words, we have surface currents which are flowing around here in the phi hat direction, and of course they're flowing all the way, they're flowing everywhere like this. Alright, so if we wanted to know what that surface current was for a particular length element of the cylinder, so let's say the cylinder, for example, is length L, and we wanted to know the total current flowing around the cylinder, we would just take K and we would multiply it by the length. Alright, so if we want the total current flowing around this cylinder, a cylinder of length L, the total current then would be I would equal K times the length, which would equal M L phi hat. Okay, so that's how this works, and this is the simplest geometry that we could study. We're going to now move on to a slightly more complicated geometry. So let's have a look at a sphere of radius r with constant magnetization. We're going to study a sphere of radius r with constant magnetization per unit volume in the z hat direction. And we're going to ask the question, what is the dipole moment of the sphere? Well, to calculate the total dipole moment, we would multiply the dipole moment per unit volume, that's this quantity here, by the volume of the sphere. It's that simple. And so the simplest way to calculate the total dipole moment, little m, is just to perform that very straightforward calculation. And there is our result. Okay. So we're going to repeat this calculation in a somewhat more complicated way, but it is useful just to see how the surface currents can be used and how they work. We're going to calculate the surface currents and the volume currents, and from them we're going to calculate the dipole moment. Now the volume bound current density is 0, and you can see that because the curl of a constant vector field is 0. But the surface bound currents are not 0 because the cross product of this vector with the surface normal, which is in the r hat direction, is non-zero. So let's calculate, first of all, let's calculate K. Alright, so I've taken the cross product of z hat with the surface normal r hat. If you're in any doubt about taking that cross product, I suggest you go and try that calculation. You can express this in spherical basis or this in Cartesian basis. There's a variety of ways of doing that, so you should try that and just verify that this is indeed correct. Okay, so having obtained K, we're going to break the sphere up into a series of current loops and integrate over those current loops appropriately to generate the dipole moment. Okay, so we're going to slice it in this way. So there's a slice through the sphere, so this is a ring on the surface, and we're going to integrate up over a whole series of rings up the sphere like this. I'm going to calculate the dipole moment contribution to each of these current rings. Alright, so let's first of all calculate the current flowing here due to this current density K. Now you remember this has units of amps per linear meter, and if we multiply by this length here, meters, then we get current. So let's do that. Okay, so there is our current flowing in around this loop here, and to calculate the contribution to the dipole moment, we would multiply by the area, A, and the dipole moment would be in the direction of the surface normal, which will be in the z hat direction. So we obtain the following. Okay, so there then is our contribution dm to the total dipole moment of the sphere. I've just noticed that I left a d theta out up here. I should put that in. Okay. And so now what we're going to do is we're going to integrate this over theta, and we're going to integrate it from 0 to pi. Z hat is a Cartesian unit vector, so that comes outside the integral. And okay, so let's perform that integration. Alright, if you do this integration, you'll find that this integral is 4/3, and so we generate the result that we had on the previous page. Okay, and there is our there is our final result in agreement with the previous result. Now, if you wish to, you can now go and calculate the magnetic field using the expression for the vector potential A in terms of M, and then you can calculate the curl of that to get the magnetic field B. I won't do that here, but it might be a useful calculation for you to explore.